Hello, good morning or good evening, wherever you are. Welcome again to IEEE Vehicular Technology Society Young Professionals Seminar. We have Dr. Jan Shadang from King's College London. She's an associate professor, and today she would like to speak about intelligent connectivity for XR-aided teleoperation in 6G. So we know like 6G is something that is very hot in the discussion today. We have been working on 5G, and we are, you can say that working on advancement in 5G right now, and we already have 5G handsets in the market. So it's very good time to speak about 6G and anticipate what is going to happen in the future. So we have a wonderful speaker. I look forward to listening to Dr. Yansha. Thank you very much, and floor is yours.
Thank you very much for your nice introduction and the kind invitation. And it is my pleasure to give a talk on the topic of intelligent connectivity for XR-added teleoperation in 6G. In my vision, one of the killer applications in 6G will be XR-added teleoperation. This will facilitate diverse applications for industrial piloting use case, for example. In the industrial use case, the workers can control the robots remotely to handle dangerous tasks without being present. In the piloting use case, you can have the firefighting commander oversee the fire situation from multiple area robots from different angles through a 360-degree video and closely follow the fire development by maneuvering the robots in real time. Through the visualization and interaction with the virtual objects, the XR can enrich the information provided for manipulators. So this will allow remote robotic control through providing a transparent human-machine interface, which will solve the human problems, transfer the human problem-solving and the manipulative skills over the internet to the remote environments. For example, you can have a doctor skills transferred to rural areas for patient treatment. In order to support the vision I mentioned above, we need to first understand the requirements and the challenges in the cellular connected XR networks as well as the cellular connected robots, respectively. So, in my personal view, the XR devices will become essential portable devices such as the smartphones for human being. So this will need to be supported by the cellular network with a seamless experience. Of course, we already defined some of the 5G requirements for the XR, but in the 6G, we will continue raise more stringent requirements because it will allow for more interesting applications such as automated video streaming, which requiring extreme capacity, crowded event sharing with the requirement on the extreme capacity, and also the 6 degree of freedom immersive content requiring the high throughput or low latency, and then the remote control tactile internet require low latency. So these are still major challenges to achieve these applications using the 5G network. That's why we have presented several corresponding challenges and solutions in our magazine paper listed as the first one, and which illustrate, for example, one challenge is how to achieve the high transmission bit rate with 4.42 gigabits per second, and how to realize low latency as low as 5 milliseconds. So on the other hand, we need to enable the cellular connected robotic networks for industrial setting. We also identify many machine learning solutions in such a massive industrial IoT setting in our work. And in my talk, I will mainly focus on the area robots as an example because it requires very accurate control and the risky of the control of it. So the design can be leveraged to other robots such as ground robots, such as AGVs or robotics arms. So to better understand the practical requirements of both the XR added teleoperation technology, we present our group's testbed in the first part of my talk, and then in the later part, I will talk about some of our machine learning works facilitate applications. So let me first present our proposed general architecture of XR-added teleoperation system in both the industrial and the piloting use case. So in the bottom figure, we have the system is consists of two parts. The first one is the robot to the XR link shown at the top, and then the XR to the robotic link shown at the bottom. So if you look at the top figure, the XR robotic to XR link, the robot's sensors will capture the environment information through different kinds of sensors, which can capture video, capture depth information, multisensory data, and tactile feedback. And then they can be delivered to the base station, and this base station usually need to be equipped with edge computation capability, so that the captured video and depth information can be processed and used to reconstruct into a 3D model and pre-render to a metadata. And after receiving this rendered model from the base station, the XR device on the right side will render and register the model with the manipulator's physical environment. So in the XR to the robot link, the devices such as haptic gloves can capture the manipulator's motion and the skeleton. And this can be transmitted to the base station, processed, and recognized as the command and for the control for the robot. So with this edge support functionality, we can enable the simultaneous localization and mapping, which called SLAM, and also command and the robot's manipulation will be able to calculate it and transmit to the robot on the right side. And under this architecture, various of physical devices can be integrated to facilitate this vision. So in our work, we mainly built two test bed. One is a UAV teleoperation test bed on the top, and then the second, the bottom one is a VR added haptic test bed. So in the UAV teleoperation testbed, the testbed contains the XR to the robotic link as well as robot to the XR link between the joystick controller and Matrix 100 UAV platform. The UAV platform will be able to receive the command and control signals and also capture the video from cameras. So the cellular network was built through the software-defined radio platform based on the USRP from National Instrument. And then the network function of the core network were running at an extra server. So for the robot to the XR link, the video will be able to capture it from the UAV side to the monitor in the operator side through the onboard connectivity platform. So for the XR to the robot link, we will be able to use the manipulator to control the using the joysticks to control the robot while through the network, and then send to the UAV through the UAV USRP base station. And the second platform, haptic robot in the haptic robotic testbed, we have a haptic robot on both sides, and it include a robot to XR link from the panoramic camera on the right side to the controller with 100 with a 360-degree VR video feed. And we will also have the depth camera getting the information used for the force, as well as the tactile device used for the force feedback. So the 360 video will be created at the center at the base station and can be fed from the depth camera to the HTC Vive on the left side of the XR device. So in this platform, I especially want to talk about the physical equipment we have used as shown in the figure. And these are when we did the experiment in the lab, we capture all the hardwares we have used. And of course, you can find in the paper more details of the testbed. So generally in the UAV control testbed, the joystick is somehow acted as a controller from, you can think of the display can be a VR, XR display as well. This is under development right now so that we can just use the XR device to control the UAV, not only using the joystick. But generally the information flow are two parts. First one is the control command generated from the joystick or the XR device, and then going through the EPC, and then delivered to the base station. The base station use the USRP to deliver the radio signals and receive at the UAV side through the blue arrows that you can see. And then you also have the camera feed coming from the UAV side from the green arrow sent to the USRP and goes through the base station to the EPC and display at the or XR device. So in this work, there are two novelty when we need to tackle different from the conventional UAV testbed. They just look at mounting mobile phones on top of the UAV and then capture or measure the performance. In our case, we want the full integration between especially the command and the control signal into the UAV side. So we built two algorithms. One is sending the control signal at the base station, and the second one is controlling the UAV UE at the UAV side. So first, the EPC will need to encode the control and the command information from the joystick and then send to the UAV side using the cellular network. And then this is done through the algorithm 1. And in the algorithm 2, we focus on when the UAV UE receive the command and control signal, and it will need to translate into the mapping to the DJI robot, DJI UAV's API. And in this way, we will be able to capture the information, the performance in much more practical way. So the first algorithm sending the control signal, the second algorithm controlling the UAV UE. And in order to allow the real-time video streaming, we also used open source server, which called the WebRTC, installed at the camera side. So the EPC can fetch the real-time video from the camera, and we can evaluate the end-to-end performance through the QR code generation and the QR code recognition. So in the next slides, I show the rough video which we captured right before the COVID, and the student did the experiment to see that if we can control the UAV in the downlink properly, and you can see the control is fine, and then on the uplink side, it's actually delivered the video with a low quality video from the UAV to the laptop. So one interesting result we find out when we evaluate the performance, when we capture both performance at the throughput in the uplink and also downlink, we captured the transmission latency for the command and control signal, as well as the reliability. So if we look at the bottom left figure, it's transmission latency for the command and the control signal versus different transmission frequency. So we can see that when the transmission frequency is lower than 40 hertz, we can see that the transmission latency is below 20 milliseconds, even with a short distance, and the high reliability almost 100%. However, if we have the transmission frequency more than 40 hertz, we see a big jump of the latency to almost 1,355 milliseconds. And also we see a big decrease in terms of the reliability. And this is mainly because the command and control transmission frequency is higher than the command and control reception frequency. And this command and control reception frequency is usually defined as the DJI matrix UAV API. So and we managed to capture these interesting observations when you cannot observe in a theoretical study. On the right side, when we evaluate the throughput of the when we look at the video transmission, we want to look at how the different elevation angle change will influence the performance. And here, the high elevation angle simply means the UAV is flying similar height as the antenna. As you see, the antenna is just on the table. And if the UAV is fly similar height with the antenna, is called high elevation angle. And if UAV are much below the antenna, is the low elevation angle. And you can see most of the mobile devices are following this low elevation angle. And the high elevation angle mainly happens when you have UAVs who have different flying heights. So the performance shows that the throughput, as in showing this red line, degrade substantially in the middle range, which is the high elevation angle. And this is because when we have high elevation angle, the antenna, the base, usually the 4G or, the antenna are designed for the down tilts for the UEs rather than for UAVs. So this requires a new design of the antenna at the base station in order to provide a better gain for UAVs at the different heights. And this kind of observation is also seen from some of the analytical studies in existing work. So we managed to capture interesting results, practical performance through the in-lab experiments. After that, I also want to briefly mention our existing work from the group, which also look at a commercial testbed, not based on open source platform, but a commercial testbed provided by Ericsson and BT Verizon, where we show that we can also fly the UAV with some collaboration. But in this case, we didn't look at the performance evaluation. That's why we are trying to see how can we propose different new algorithms at both the base station side and UAV side to enable more intelligent control, fulfill the stringent requirement at the UAV platform. So next, I would like to also talk about the wireless AR networks as part of the XR Teleoperation, because VR, AR, and MR will be one of the future services, also in the 6G, 5G, and 6G. So right now, most of the conventional VR services are based on some existing videos resource that already been computed. But here we are more interested in the interactive VR experience, this means that we need a real-time feedback. We need the human's response will change the video they want to watch. So this will raise a very big requirements on the VR interaction latency. At the same time, the transmission of the VR video is totally different from conventional video, and we will talk about this later on. So in such a wireless VR scenario, it also have a unique challenge of in the uplink and downlink, they have a different data rates requirements due to the different type of data. So I will talk about this in detail later on. And generally in this part, I would like to mainly focus on the machine learning solutions that we propose for the wireless VR networks. So here is some of the backs. One of the important part of the VR video streaming is the VR rendering. This is because the VR rendering requires a very computational intensive capability, and it actually focuses on how to perform the transformation from a 2D video to the 3D video, such as the figure on the left. And you can see that the 2D horizontal figure are somehow converted into a 360 degree video. And this process first consume a lot of computation resource, and also it will takes a lot of time to do that. Um, so that's why in this work we will focus on the VR rendering, because of the unique task only exist in such kind of services. And in reality, human when they are wearing a VR devices, they will only watch a portion of the video rather than 360-degree video, as shown in the middle figure. So this partially observable video, we call it as a field of view, and as shown by the circle blue color in the middle figure. And it's also mapped to the 2D environment on the right figure, which are the blue blocks, and this include all the tiles are in the field of view of the human eyes. So rendering the 300-degree video in real time will be very costly, both for the downlink transmission as well as the computation. So one potential solution is to only render the requested field of view each time based on the uplink information from the human, from the VR user, which include the head or eye movement. And with that, we can compare two cases where most of the existing work have been considered the VR video rendering task occurred directly at the VR device. And when the rendering function is processed at the VR device, then the 2D image, 2D video will need to be continuously delivered to the VR device while the wired or wireless transmission. And then the VR device will render the video from the 3D received image to the 3D video locally. And this will be very costly. Imagine that you have more VR devices who are much lightweight, then the computation power may not be able to fulfill such a high computation requirement. So that's why we think maybe we should move the rendering, such a computation intensive task, to the edge side. And in this way, if we move it to the edge side, the staged 2D image will be rendered to the required field of view through the ERP mapping. This mapping is for transferring the 2D to 3D video. And then this field of view can be it will be able to downlink transmit it to the users, and we can use unicast or multicast, depends on the user's preference. If the user requesting the same field of view, they can be in the same group using multicast. If they are requesting a unique field of view, they will need to be delivered using the unicast. So shifting the field of view rendering task from the VR device to the MEC may not only alleviate the computation requirement at the VR device side, but also decrease potentially the VR interaction latency for devices who are requesting the same field of view. So in the conventional wireless VR system, if you look at the whole system, the VR user usually first transmit the tracking information, such as their head or eye movement, to the server through the uplink. And then the server will be able to use the rendering task through the ERP mapping and convert it to a 3D video, and then it will be able to transmit to the VR user through the downlink transmission. And of course, if in this case, the server can predict the requested field of view preference, we probably will save more time for the VR interaction latency. And I will talk about the definition of VR interaction latency later on. So Before I do that, because prediction is a such important point, so I would just want to briefly mention our work published in TVT on this viewpoint prediction, and then we will focus on the whole scope of the uplink, rendering, and the downlink. So this is our considered scenario where we have a wireless VR system and we have a base station. It can be a small cell base station, connect to the core network through a fiber link that serve a K number of VR users through wireless connectivity. So the base station is equipped with M antennas, and the VR users right now we consider single antenna, and we can use maximum ratio combining to combine the signal for uplink reliability at the base station site. So in the data size, we actually use real data collected by University of San Diego, who actually recruited 153 VR users to watch 16 types of video, which range from sports events to landscape content or entertainment. And the human's preference of the head movement and eye movement are tracked for all these experiments. And we managed to analyze this data. They kindly share the data, and we analyze the data and managed to obtain map into three important viewpoint information. One is pitch, yaw, and roll corresponding to X, Y, and Z. And we managed to find the user's preference. Each line in the figure corresponds to one user's viewpoint preference. And this one is the X angle distribution, and this one is the Y angle distribution of the all user, and the last one is the z-angle distribution of all user. So we take one example of the x-angle distribution for our data, and we use for viewpoint prediction. So different from the viewpoint prediction, which just look at the prediction itself, we consider the both the learning prediction performance as well as the uplink transmission performance. So traditional scheme, or when they want to guarantee the uplink transmission, when there is an error, we actually capture this in the uplink. So in the 3GPP, they already look at, when you are uplink transmitting the viewpoint is a small packet. So we can look at some of the conventional scheme, which is a grant-free scheme, to transmit the small packet. And one scheme that very interesting is the proactive transmission scheme standardized in 3GPP. And it simply means that the VR user will need to send the viewpoint to the base station multiple times. And then the base station will process it and send the ACK or NACK feedback to the VR user. So only when the base station successfully decode the signal, the viewpoint, and send back to the VR user, then it will send the ACK. Otherwise, they send NACK. So we can use the ACK and the NACK information to know if the user has information has been correctly received or not. So with uplink, we want to look at using the proactive retransmission scheme. How can we use the online learning approach that can obtain a accurate viewpoint to update the parameters and predict the viewpoint for the future time slot? So the optimization problem becomes how to minimize the prediction error between the predicted viewpoint and the actual viewpoint in the next time slot. So to predict the viewpoint of VR user in the next time slot, we consider a sliding window which capture not only the current viewpoint but also the previous viewpoint for several time slot, and we compare several simple learning regression or neural net and a recurrent neural network based on LSTM or GRU, and we use this method to capture the time correlation of the viewpoint of the VR user in continuous time slot. So in this case, the output will be the predicted viewpoint for the next time slot. And this is optimization problem where we look at average or average all the arrows that we have received for all the number of users. And because we have a large amount of data sets, we have almost 1,000 data samples in the VR data set. So we consider the K-cross validation method to ensure that all the data sample have the opportunity to be tested and avoid biased performance. So, to the best of our knowledge, I mean, there's for the research that works that consider online learning, they always assume that the edge server can directly obtain the data through the uplink transmission without error. But in our work, we consider the transmission error, but we also consider how to minimize the transmission error using the proactive transmission scheme for the small data transmission in the uplink. And this is the detailed algorithm for our online learning approach, and we can use it for both the neural network GRU and also for the linear regression. And for the simulation result, we managed to obtain the prediction error for different number of training user, and we find out that when we increase the number of users, of course, the training prediction error can be decreased a little bit. And if we compare different schemes, we see that our proposed LSTM scheme, the blue color, and then the GRU scheme, the green color, can achieve better performance in terms of prediction error and much better than the black ones using the gene edit method. And we also compare those methods with proactive transmission scheme and without proactive transmission scheme. So we can see that with proactive transmission scheme for all the method, it is show as the solid line with it is show that it can improve the performance compared with the dash line without proactive scheme substantially. So it means that with the joint design of the transmission as well as the online learning method, we managed to reduce the prediction error in the uplink for the viewpoint prediction. After that, with the uplink considered in this work, we want to also consider full loop of the VR interaction latency, looking at exactly what video we are trying to deliver and the unique characteristic of the VR video. So we focus on the MEC-enabled wireless VR network. And in this work, we consider such a scenario, very simple scenario where we have, we first, in this work, we don't want to divert the focus. So we assume that the uplink transmission without error, because we already addressed the transmission error in the last work with the real-time data. So here we want to look at just how the downlink and rendering, and also we consider the prediction, but the uplink transmission is error-free. So in this scenario, we have a cloud server connected with multiple MEC servers. And the reason we have a cloud server, of course, it will help us to do some learning if we are having a centralized approach. And we need a fiber link between the cloud server probably with the MEC, and then the MEC will be able to serve different VR users in this framework. So different from the computation, the rendering at the VR device, we consider the rendering at the MEC. As we mentioned, if we do that, the rendering task will be able to convert the 2D image using the ERP method to field of view, and this field of view will be able to deliver to the downlink to the user. And if we are consider the uplink, consider render at the VR device side, we need to deliver in the downlink the full 2D stage image to the user, and then the computation rendering happens at the VR device. Except from that, we also consider model migration. And here the model migration means that if there are multiple MECs who are requesting the same field of view, processing the same field of view, then probably I just need one MEC to perform the rendering task, and then I can deliver this computed field of view to other MECs through migration. And in this way, we save the time for and energy for all the edge server to compute the rendering at the same time. So if you want to fairly compare these two, we need a model for the calculation of the data size change between the 3D to 2D video. And we had a model in the paper. And we also need the time consumed for each step. Because if you look at the bottom figure A, usually there are 4 steps. In the uplink transmission, you transmit the viewpoint, and then you have the MEC render, or you have the render happened at the VR device, and then you have the migration, if you want a migration between the edge server, and then in the downlink of the transmission. So depending on which schemes you are using, this time calculation of the VR interaction latency change. And here we can see the left side is the MEC rendering scheme, the right side is the VR device rendering scheme. Compared with MEC rendering scheme and VR rendering scheme, we can see that there are difference in the time calculation. And if we look at one by one, the one we are trying to propose will be the optimal approach. We think is the MEC rendering scheme with prediction and with migration as the before. And if in this scheme, with prediction, we will not need to wait for the uplink transmission. So uplink transmission time is removed as a red block, and we only have the rendering time, at the MEC, the migration time, and the downlink transmission time. And if you have a consideration of without prediction, then you need to add the uplink time as the B1 and the B2 scheme. So the red blocks are added, which means you need to wait for the uplink transmission, and then you can perform then you know which viewpoint the users want to select, and then the MEC will be able to start the rendering process. And if we consider the migration and without migration, of course, the only difference is the migration time will be removed if you consider without migration. And if we look at the comparison with the VR device rendering scheme, without prediction, we have the time required for the uplink transmission. The rendering, we need to have the downlink, the rendering time at the device side, and also the downlink time will happen first, because you need to first have the downlink transmission of the 2D stage image, and the rendering happens at the VR side once you receive this 2D image. So we compare these 6 schemes in our work to see the efficiency of the different schemes in the same domain. So the problem becomes how to optimize the quality of experience of all the VR users based on the mean square error. And we define the mean square error as a binary function to represent the field of view can be rendered or delivered within VR interaction latency or not. So we are not only caring about quality of experience, but also we are looking at the time constraint, which is the VR interaction latency, including the uplink, downlink, and the rendering time. So based on this system model, we formulate the problem as shown in the second part, which is maximize QoE performance. And we want to we use the define the PSNR value to capture the quality of experience, and then we want to make sure that the TK, which is the VR interaction time, is smaller than the threshold. So in the learning part, we propose to use decoupled learning strategy, because here the problem is how to manipulate, how to choose the correct MEC to serve corresponding VR user. And also the MEC should select which field of view to render depends on the request of the VR user. So in this decoupled learning strategy, we consider both the rendering and the association to make a accurate decision on these two in real time. And we, of course, we still want to reap the benefit of the prediction. So we use GRU because we show that GRU achieve a good performance in terms of prediction. So GRU is used to predict the field of view for the method with prediction. And then according to the predicted field of view and the location of the VR user and the computation capability of MECs, then we can select the proper MECs using the deep reinforcement learning approach. And here we consider not only the centralized approach, but also the decentralized approach, DQN and the AC. So we consider the distributed learning approach simply because in some cases we have the MEC only observe the information in his network, so he will not be able to know other information observation from other MEC. So they have to make the decision independently based on their limited number of observations. So the distributed learning scheme are distributed deep reinforcement learning schemes are used to for practical implementation, whereas the centralized approach will need to rely on the cloud server to help the centralized information sharing, and we want to compare the benefits of this performance in our work. So in the reinforcement learning part, in the state, we use the captured information of the location of the VR user and the distance between them, and also the computation capability of each MEC. Here we consider different computation capability at each MEC. And the action space is simply whether the whether a certain MEC should be rendering which field of view and serve which group of VR users. And the reward is used as the PSNR value for all the, so we are trying to maximize the total QoE. So we actually take the sum of all the VR users QoE performance. And in this, this is the result. We show the converged performance of four approach, and we compare centralized distributed approach. They are all converge with different speed. Of course, centralized approach converge much faster. And we the most interesting result we actually compare here when we look at the VR interaction latency of each VR user. This is an average performance of each VR user, and we compare the MEC rendering and the VR rendering scheme. So the MEC rendering scheme are the ones, VR rendering scheme is the green color curve, and other colors are MEC rendering scheme. We can see that the VR interaction latency of the MEC rendering achieve 40 milliseconds, almost more than 40 milliseconds scan in the VR interaction latency compared with VR rendering scheme. And we also see that our proposed approach, which is MEC rendering with prediction and with migration, as shown in the blue curve with circles, and this one achieved the lowest VR interaction latency performance, and it also doesn't change with different uplink transmission latency because we use prediction, so we don't need to wait for the uplink transmission. And if we compare with our dynamically associate scheme with the nearest association scheme in the dashed line, we also achieve a very substantial gain of our performance. And we also plotted the VR interaction latency versus different number of MECs. So interesting, we see that, of course, increase the number of MEC, we can have a better latency performance, but somehow it was stable at a certain point, because as um, I mean, when the number of users increase, of course, the VR users have more MEC to choose, so they can select the MEC with a higher computation capability to render their required field of view. This will reduce the latency. However, when the number is too large, all the MECs, the preferred MECs, has already been activated for rendering and the downlink transmission, which leaves very little room for improvement. So due to that, I think I reached the 45 minutes. I just want to briefly mention two works that I have, two other works that in this domain. So first one is we on top of the first two work, we look at the terahertz RAS assisted terahertz transmission for the wireless VR scenario. Consider how to optimize the phase shift of RAS in non-offside or line-of-sight scenario. And here we also propose a more this is the figure. We consider the long left side, the left side based on the obstacles, the human blocking other humans' view, and we use this information to actually with the arm to optimize the QoE performance with a different definition. And we propose a more complicated learning approach where we actually generate different maps based on the location of the user, the MEC and RS, and also the status of the each grid used as an input for the convolutional neural network to predict the line of sight or non-line of sight of each location of the user. And then we use a constraint reinforcement learning, where the constraint is the latency, VR interaction latency, to guarantee the VR interaction latency under a certain limit. And the goal here is how to optimize the phase shift to achieve good performance of the QoE. So these are part of the CNN and the deep reinforcement learning approach with the design of the state, action, and reward. And our result finally show that in the right figure, our constraint deep reinforcement learning approach, as shown in the line of the black line, can nicely have a very low VR interaction latency. If with prediction, the pink line will be able to further reduce the VR interaction latency and achieve a good QoE performance, as shown in the left side, achieve almost near performance as a gene-edited method. So and the last work, we look at a more teleoperation use case where we have multiple UAVs interact with the VR user through the access point, delivering the 360 video. And we use a multi-agent reinforcement learning approach to group the access point, make sure that the access point, they decide to collaborate with other access point or not to serve the users. And we also consider the scheduling of the tilts, and we especially one novelty is we actually look at how to schedule the tilts for correlated user using the hierarchical deep reinforcement learning, where the scheduling task is done at the meta controller, and then the association of the user to the access point is done through the deep reinforcement learning as an other agent. So in this approach, we also introduce the distributed learning approach with a more complicated learning design. And due to time constraint, I will just skip some of the details here. And at the end, it's the step we look at the scheduling, association, the uplink transmission between the UAV and the access point, and the access point to the VR users in the downlink. And we have lots of mathematical model to model the simulation environment and also formulate the new QoE performance based on each tilt rather than each field of view. Here is based on the unit of tilt. And at the end, we propose more novel learning algorithm based on the Rainbow deep reinforcement learning multi-agent system with a mean field theory. And we also use a convolutional neural network to capture the access point, the position, UAV position, and the scheduled tilts for the output of the information to help the Rainbow agent to make a better decision in terms of cell association and the scheduling. And we compared with the cell-based method and the cell-free method. Cell-based is just single cell, and cell-free means all the access point collaborate. But in our method, we dynamically decide the access point that they collaborate or not for serving different users. And we use federated learning to make sure that the distributed multi-agent reinforcement learning can converge. And here is our converge result. And we can see on the right figure, if we don't use federated learning, the red curve is the distributed reinforcement learning will not converge. However, the hierarchical reinforcement learning will be able to converge even without federated learning help. And our results show that our approach, the black line and the red line, one is the distributed deep reinforcement learning with federated learning approach, and the hierarchical deep reinforcement learning with federated learning approach achieve better quality of experience compared with the cell-free approach as the green line and the cell-based approach as the purple line. And here you might see that the centralized approach is worse, and the reason is that we consider a reduced area of observation, which is a not fair comparison. I should have removed this line, but in reality, centralized approach should outperform the distributed approach. But in practice, we cannot reinforce the centralized approach because each exercise point will need to make the decision by themselves. So at the end, I would like to acknowledge my collaborators and the students working with me. And thanks for your attention. And if you are interested to know more information, feel free to email me with more details. Thank you. Hello?
Hello. Yes, can you hear me?
Yes.
Okay, thank you very much. It was a pleasure and a very interesting talk. We didn't have many questions on the board yet, and we can wait for a couple of minutes while I can ask one thing. It's. There are many interesting aspects, but one thing I was thinking, for example, when we were
Mm.
considering number of MECs, in reality, we know like there may not be that many MECs deployed
Yes.
close to one mobile user
Mm.
or a drone user. So, did you make any assumption like what could be the realistic number and how do we translate the performance accordingly?
That's a very good question. So here the figure is the number of MEC. So we use the 8 to 24. And
Mm-hmm.
we can see that from 20 to 24, the performance gain is not too much. So it really depends on the number of users as well in this network. And of course, how to optimize the number of MEC and the location of MEC is another question in the practical setting. But here we are trying to say that how this number of MEC will influence the latency performance and the QoE performance. At least we show that, uh, substantially increasing it without a reason doesn't make sense. You need to consider the trade-off between the cost of deploying the MEC as well as the performance gain you can obtain.
Mm. Yeah, exactly. Because that is what I was thinking as well. I think it will help the network operators to design or decide how many MECs they would need in a certain area.
Yeah,
And
so we will be able to run this learning algorithm because it already optimized. So we can see that the maximum with the dynamic association between the VR user and MEC, what's the best performance we can achieve. And then maybe, for example, this one in this setting, maybe more than 18 or 20 MEC is not important anymore. You should not deploy more than that.
yeah, yeah, good.
Thank
And
you.
for example, one more thing, like for our viewers, if they would like to collaborate on or speak with you on any of the topics, then are you willing? Like your group is willing to collaborate?
Yes. We are. I mean, our group are closely working with industrial partners, and we have worked with Ericsson, Huawei, and many other companies, and we are happy to work with any topic for research collaboration.
Sounds good. Sounds good.
Mm.
So this is an important message for our viewers that if they have some ideas in the same direction or something related to this, you are welcome to reach out to Dr. Yansha. I think they have a wonderful group. I know many of the researchers personally, and they're doing some great work. Once again, I would like to thank you for
Thank
today's
you.
talk, and please feel free to share with your colleagues and students the link, and I think they will all benefit from it.
Yeah, no problem. Thank you.
Thank you. Have a good day.
You too. Bye.